In this section 8.5 video, I'm going to cover triad examples 1, 2, and 3, which talk about conic sections in polar coordinates. You've had a very brief introduction to polar coordinates, so if this is feeling a little shaky for you, I wouldn't worry too much about it. We're just going to go over the very basics and the necessary steps you need for this class. I also want to mention that you will not be responsible for computing cosine or sine of any values in your head or by hand. You can always rely on your Desmos scientific or graphing calculator in this class. So in trait number 1, we're given an equation here. This is a polar equation. Notice we no longer have x and y. Instead, we have r for the radius and theta for the degree. So that r is going to represent how far our graph is from the center, and theta is going to represent its rotation about its center. But all we're responsible here is identify the conic. So is it an ellipse, a hyperbola, or a parabola? We want to find the directrix, and we want to find the eccentricity. So let's go ahead and first try to get this into standard form. So the standard form of our conic polar equations has this first constant value in the denominator as a 1. So I'm going to rewrite this equation with a 1 in the denominator here by multiplying the entire equation by 1/3 in the numerator and 1/3 in the denominator. So we'll do in the numerator 2 times 1/3. In the denominator, we'll have 3 times 1/3 minus 1/3 cosine of theta. Simplify this down a little bit. We have 2/3 in the numerator. We have our 3 and 1/3 cancel out to be 1 minus 1/3 cosine theta. So now this is in our standard form for a polar equation for a conic. So what we need from this equation is first to determine the form of the directrix. So notice here we have a cosine function. If we have a cosine function here, this means our directrix is going to be of the form x equals something. Since we're dealing with a negative value here, we're subtracting 1/3 cosine theta, we're going to have a negative and then p. So we'll need to find out our value for p, but we'll set that aside for a moment. This is going to be the form of our directrix. We also need to find the eccentricity, and if we find the eccentricity, that's going to tell us exactly which type of conic we're dealing with. So the eccentricity is going to be this value right here. So E is going to be equal to 1/3. If our eccentricity is less than 1, we are going to be dealing with an ellipse. So we know the type of conic and we know the eccentricity. The last thing we need to do is finish writing the equation for our directrix. To do this, we need to solve for p. So the numerator of our polar equation in the standard form is E times P. So E times P is going to be equal to 2/3 in this problem. We already said E was equal to 1/3. So 1/3 P is equal to 2/3. Multiply both sides by 3 to cancel out that 3 in the denominator on the left side, and we'll cancel our 3's on the right side as well. And now we have that P is equal to 2. So just to recap, our conic is an ellipse because the eccentricity is less than 1. Our eccentricity is equal to 1/3 because that's going to be the coefficient value in front of our cosine or sine function. And then we solve for P by recognizing that if this equation is in standard form, which it is, the numerator is going to be E times P. So our final directrix is going to be equal to x equals -2. Now let's try graphing one of these polar equations. So we have the graph of r equals 2 over 4 minus cosine theta. Let's head over to our Desmos graphing calculator to see what this would look like. You should have already seen how to graph a polar equation in the Learn Desmos polar graphing video, but we're going to go through how to do it again here, and I'll show you how to change the axes to polar coordinates instead of the rectangular coordinates we're looking at right now. So our function was r equals 2 divided by 4 minus cosine theta. Let's zoom in a little bit here. So here is our ellipse that we're working with. When we specify r and theta in the Desmos graphing calculator, it automatically recognizes polar coordinates. So make sure if you're trying to graph in polar coordinates, you don't end up with an x and a y in your equation. So we can graph on top of our rectangular coordinates here just fine, but if you wanted to look at this in terms of polar coordinates, so in terms of r and theta, you can change this by clicking on the wrench icon in the upper right corner, and you'll see under the word grid, there are two circles. One looks like a rectangular grid, and then to the right of that is this spider web looking feature. If you click that, it will change your axes to polar coordinates. So the distance from the center of the origin here represents r, and the angle that those lines are going out at represents theta. For our last example, we are asked to find the polar form of the conic given a focus at the origin, E equal to 1, or eccentricity equal to 1, and a directrix at x equals -1. So let's do a quick sketch of this. Here is our axes, our x and y axes, and we have a center at the origin. So here's a focus at the origin. Our directrix is the line x equals -1. So the line x equals -1, that's going to be a vertical line right about here. We also know that our eccentricity is equal to 1. This means we are working with a parabola. Since we have a parabola and we know that our focus is right here and our directrix is here, parabola is going to be sketched open to the right, something like that. So now we want to write the equation for this in polar form. We're always going to have r, or the radius, on the left-hand side. General form is going to be e p over 1 plus or minus, and then we need either the sine function or the cosine function, and that is dependent on the directrix. So the directrix is a vertical line. Recall, x equals -1 is a vertical line. Therefore, the function that we're going to use is going to be the cosine function. So we're going to have e cosine theta. Well, we know that e is 1, so we can replace the e's in this problem. So we're going to have p over 1 plus or minus cosine theta. To determine whether this is going to be a plus or a minus, we need to look at the sign in the directrix. And we see here we have a negative sign in the directrix. So our sign in the denominator of our function will be a minus sign. So we're going to have p over 1 minus cosine theta. All that's left to do is to find p. And to do that, recall that our directrix has the value of p in it. So the numerical value in our directrix, which is 1, is going to be p. So lastly, we can write our parabola equation as r equals 1 over 1 minus cosine theta.